Okay, welcome back. Today we're going to talk about uh, chapter 3, which is about vectors and coordinate systems. And this is going to stick with us for the rest of the semester. And if you're going to take E&M, it's going to stick with you then, and basically forever, if you're in science and engineering. So we're going to talk about, first of all, we have two distinct quantities here we usually deal with in physics. You have scalars and vectors. So what's a scalar? A scalar is a quantity that is simply described by just a single number, with units, of course. What are examples of scalars? For example, the mass of an object is a scalar. So if you say an object has a mass of 1 kilogram, that's it. You have fully described it. There is no additional question about its mass. If you say the temperature here is 70 degrees, then you have fully described it. And so on. Distance, the height of a person, for example, my height, the volume of an object. Let's say something is 1 gallon of volume or 1 cubic meter. That's it, you have fully described it. There are other quantities that need more than just one number to fully describe, because in addition to the fact that they have a magnitude, they also have a direction. For example, the force on an object is both magnitude and direction. So it matters, for example, this piece of paper is, if I push it towards you, it matters of, if I push it very hard, that matters. And also it matters whether the direction, if I push it this way, it will move this way. If I push it this way, it will move this way towards you or away from you. So what matters is actually two things, the magnitude of the thing and the direction. In general, vectors can be in any number of directions. They could be in one dimension or even 0 dimensions. Or what we deal with usually is 3 dimensions or n dimensions, as mathematicians like to talk about. In general, it's just n dimensions. And so in 3 dimensions, which we usually deal with, you need 3 different numbers to, or not different, 3 numbers to describe to represent the magnitude and direction of a vector. You have to tell it in how much of the vector is in 3D space. We talk about x, y, and z. So how much of the vector is along the x direction, how much of it is along the y direction, and how much is in the z direction. So so you need in 3D, you need 3 numbers to represent the magnitude and direction of a vector quantity. Vectors, they satisfy 2 distinct operations called addition and scalar multiplication. So we can add vectors in a certain way, and then we can multiply them also by scalars, and they satisfy certain conditions which I have listed here. The collection of all vectors, so this is just for completeness. So the collection of all vectors with the 2 operations, addition and scalar multiplication, they define what's called a vector space. So a vector space contains all the vectors that we have and that satisfy certain conditions. It's called a vector space. Properties of vectors. We usually denote a vector with a letter and an arrow on top of it to distinguish it from a scalar, right? A letter with an arrow on top of it. The magnitude of the vector A in this case, you can put A with the vector sign with absolute values around it to denote the magnitude. You can just, this is the magnitude of A, maybe it's 5. Or you can just simply write the letter A with no vector sign on top of it, and that's fine also. That means the magnitude. Now, to represent a vector geometrically, we can simply draw an arrow in the direction of that vector. And the size of the arrow, if the vector, let's say, is 2 units, then the size of the arrow will be 2 units, for example. If this is 1 unit, so this is 2 units. The size of the arrow will be 2 units, so the magnitude is 2. And the direction from the tail to, this is called the tail of the vector, this is the tip of the vector, and it points in the direction of that vector. So if I draw another vector that looks exactly like A, but instead of drawing it here, I draw it here. Right? It points exactly in the same direction, and it's also 2 units. So these 2 vectors are the same. Even though I drew this one here and drew this one here, they have the same effect. It doesn't matter where you draw the vector, as long as you draw it in the same direction and it has the same size, it is the same vector. Okay? And we'll talk about coordinate systems in a moment. But let me describe these things here. The vector addition, the conditions here that the vector needs to satisfy mathematically. And we're going to use them, but we will basically, you don't have to memorize these. They just tell you that things will work the way you think they will work. Okay? So first of all, I will talk about the geometric description. So first of all, vector addition, it's commutative, meaning if I have vector A and I add to it vector B, it doesn't matter if I do A plus B or B plus A. Just like with regular real numbers, if you have 5 plus 7 or 7 plus 5, it is the same. So geometrically, what this means is the following. So let me do these one by one. One by one, I'm going to draw that in here. So for vector addition, let me just show you here. Here is vector A. Let's say here is vector A. Right, here is vector A. And here is vector B, let's say. Let's say vector B is in this direction. Here is vector B is in this direction. And I want to add them. The way we add them is by drawing, you can draw the tail of vector B. So vector A takes you from here to here, and then vector B takes you in this direction. This is vector B. And so this is A plus B. Or I can do B plus A. So if I do B plus A, so let me draw B in here. Let me draw B here. Here is vector B. I can do B and then I add to it A later. Either way, I go from here to here and then from here to here, or from here to here and then from here to here. That's the same. That is, the end result is I started here and I ended here, and that's called the vector C. I call it just vector C. So that's geometrically how you add vectors. So it doesn't matter that, meaning A plus B is the same as B plus A. As B plus A. All right, it's commutative. Okay. All right. So, by the way, the subject that deals with vectors is linear algebra. You may have had it already, some of you. If you haven't, and you don't have the intention to take it, I would suggest you highly recommend taking the course. Okay. So now the next property here is the associative property. If I have three vectors, A plus B plus C, I can add A and B and then I add to them C, or I can add B plus C and then I add to them A. It doesn't matter. It's associative. And again, geometrically, you can represent it as the following. Let's say I have, here is, let's say I have here vectors, let's say here is, let me see here, I want to draw it exactly like here. It's hard to draw, so let's say this is vector A, and let's say this is vector B, and let's say vector C looks something like this. Here's vector C. I can do B plus C and then I add to them vector A. So let me do it as well as I can. If I do vector B plus vector C, so here's, if I do this, if I want to do A plus B plus C, let me first add B to C. So here is B. Let me try to draw it. So here is vector B. Okay. And here is vector C. I want to add them, so I need to put the base or the tail of vector C at the tip of vector B. So here's vector B, here's vector C, and then finally I add to them vector A. Vector A points in this direction, so here's vector A. Vector A. What's the end result? The end result is I have a vector that points in this direction. I will draw it in red. I will draw it in red. I end up with a vector that points in that direction. Or I can do it the other way. I can add A to B and then I add C to it. So A plus B first, and then I add C. So let's see how that works. So let me draw vector A first. Here's vector A. I can add to it vector B. Vector B points in this direction, so let me put the tail of vector B at the tip of vector A. So here is the tail of vector B. The tip of vector A. Here's the tail. And then I would add to them, this is A plus B. A plus B. That's the result of A plus B. And then finally I add to it vector C, which points in this direction. So here is vector C. Here's vector C. So what's the end result? Well, this is A plus B, and I added to it C. So I started here, we went like that. So you got a similar vector to this. So it's the same result. So this is qualitative. This one here says there exists an element, and it's unique. And it's called the identity of addition. It's a zero vector. It's a vector that has zero size. And it's called the identity of addition. So there is a zero vector such that A plus the zero vector is equal to 0 plus A because it's commutative, and it's equal to A. And then there is an inverse element for every single vector. There is the inverse of that vector. And it's unique also. For every A, there is a negative A such that when you add A to negative A, you get 0. Geometrically, let's say geometrically, if this is vector A, and I add to it, I want to add to it vector negative A. How does vector negative A? Well, it's exactly like A, but in the opposite direction. So this is the vector negative A. If I add them together, you just get 0. It's a vector that just has no size. It will look like this, just a point. It has no size, no direction. So it's just 0 vector. That's what that is saying. Scalar multiplication now. B times C times A is the same as B times C, and then you multiply it by A. So let me show you how that works. Let's say, by the way, B and C here. So it says B times C times A is equal to B times C times A. B and C are real numbers. So here is an example. Let's say vector A is 1 unit. Let's say here is vector A. It's 1 unit. And let's say B is equal to 2 and C is equal to, let's say 3. All right, C is 3. So if I do C times A first, C times A will give me a vector that is 3 times the size of A. So it's 3 times. This is C times A. And then if I multiply it by B, I will double this vector. So I would have a vector. So that's C times A. And then when I multiply by B, I just double that arrow. So I end up getting this. Or I can just do B times C, which is 6, and then I get 6 times the vector A, which is exactly the same result. Okay? And then it's distributive with respect to vector addition, or it's distributive with respect to scalar addition, and then there is the identity of multiplication. 1 times A is equal to A. So I'll not spend too much time on those. I want to now get to coordinate systems and how to set one. And then we will talk about basically how to deal with vectors operationally. I know that this is very theoretical. These are the axioms or the assumptions about vectors and vector spaces. And we will not use them directly. They're used in math to prove different results, and everything basically follows from these that we need to know. So they might seem dry or even silly that I listed them, but I needed to. All right, so now let's go to talk about coordinate systems. I will just describe it, and then I will start talking about vectors and unit vectors and so on. So first, coordinate systems, there are many different coordinate systems, And the most familiar ones, and the ones that we will use mostly this semester, is called the uh, Cartesian coordinate system, where you have the x-axis and perpendicular to it, you get the y-axis, and you get the z-axis perpendicular to both. And so to choose a coordinate system, you need basically four things. You need an origin, you need to choose your axes, you need to choose where the origin is, where is the zero, basically where all the axes meet. And then you have to choose the axes, and then you have to choose what is a positive direction, in what direction is the positive direction. And then you have to choose unit vectors. Unit vectors are the same, are vectors. Let's say you have vector A that points this way. A unit vector will point exactly in the same direction as vector A, but it has size 1 because it's a unit vector. It has length 1 unit. Okay, so it has size 1. And there are different, again, coordinate systems. There is the Cartesian. In 2 dimensions, you get the polar coordinates. In 3 dimensions, you get the spherical coordinates, the cylindrical coordinates. In electromagnetism, you might deal with cylindrical and Cartesian. In this class, we will deal with basically Cartesian coordinates, maybe polar coordinates, Okay, so let us get to some of the examples. So here is a first example here. Suppose I walk 4 miles east and then 3 miles north. Okay? So 4 miles east and then 3 miles north. So again, to describe the motion, I have to choose a coordinate system. So my coordinate system will look like this. Here is the origin. Here is the x-axis. And here is the y-axis. Here's the y-axis. And I said I would walk 4 miles east. 1, 2, 3, 4. Okay. 1, 2, 3, 4. And then I would walk 3 miles north. 1, 2, 3. I would walk 3 miles north. So we went this way first. And then we went this way. Right? So here is the direction of motion. We walked this way 4 miles, and then we walked this way 3 miles. If I say, what's the distance walked? You would say 7 miles. I have walked 7 miles because 4 plus 3 is 7, right? Is 7. Now, how do I describe this using vectors? If I ask you, what's your displacement? If somebody didn't know what you did, they closed their eyes for the entire walk. So you started here. When they open their eyes, you're here. So as far as they are concerned, this is your displacement. You went from here to here. So I would call the first displacement as vector A, the first part of the walk as vector A, and the second part of the walk as vector B, and the result is vector C. So I have this vector C is equal to vectors A plus B, right? The two vectors A and B added together. So how do I describe this? How do I give it a numerical form? So I know that the size of vector A is 4 units, and it's along the x direction. It does not have any y direction. So I can just use words. I can say vector A is 4 units in the positive x direction, but there is an abbreviation for that. So vector A, we can write it as 4 units in the x direction. How do I say the x direction, the word x direction? We will give it the letter I with a hat. This is a vector that's a 1 unit long vector along the x direction. So 4 times the unit long vector in the x direction gives you a 4 unit long vector along the x direction. The vector B is 3 units long, so it's equal to 3, but in what direction? It's in the y direction. So what do I call the y direction? Well, the people chose ij. So a unit vector in the y direction is called j, and in the z direction it's given the symbol k. Some books, by the way, they use X hat. Yeah, by the way, this is called the hat. I hat, J hat, K hat. Some books use X hat to mean the X direction, Y hat to mean the Y direction, and Z hat to mean the Z direction. Most of the upper division physics books do that, and I like that actually, but let's stick to what our book is using, I hat, J hat, and K hat. Okay, so those are the two vectors. So let's add them. So the vector C is vector A plus B. Vector A is 4I hat. Vector B is 4J hat. I'm sorry, 3. Just 3. Vector B is 3. Okay, 3J hat. If I want the size of vector A, the magnitude of vector A, which we symbolize by vector A with absolute value signs, or just A. Well, the size of that, it's 4 times the size of I hat, but I hat has size 1, so it's just 4. And the size of vector B is given the symbol like this, and it is B, and it is just 3. How about the size of vector C? We know that vector C is 4I hat plus 3J hat. So the size of vector C is just vector C. And in general, to find it, or just the length this is 90 degrees, and we know by the Pythagorean theorem that it would be this side squared plus this side squared, and then you take the square root. So it will be, formally, it will be the x component of the vector squared plus the y component of this vector squared. And so it will be the x component of C. By the way, these are called components. The one that's in the x direction is the x component, and the one that's in the y direction is the y component. So it would be the x component is 4, so 4 squared, plus the y component, that's 3 squared, square root. 4 squared plus 3 squared is 25, and the square root of 25 is 5. And it's always positive because it's a magnitude. And since we're dealing here, since it's miles, its distance, it would be, its length, it would be miles. So the magnitude of vector C is 5 miles. So the displacement is simply 5. The displacement is 5. If you walk this way and then this way, your displacement is the final position minus the initial position, where you ended with respect to where you started. Okay. So that's our first problem here. Okay. All right. We will look into more problems. Let's get to the next one. So in this next problem here, we're told you got a bird that's flying, and they say it was observed to have an acceleration of 6.0 meters per second squared at 30 degrees south of west. And it says here, find the x and y components of its acceleration. So, solution. By the way, I already did displacement. Displacement is a vector. Velocity is a vector because it has to do with direction. You say, I'm moving at 5 meters per second. If you say my speed is 5 meters per second, that's fine. That's your speed. But then if you say my velocity is 5 meters per second, I will follow up and say in what direction, because velocity is a vector. The same thing with acceleration. The magnitude of acceleration is 6. The direction is at 30 degrees south of west. So what are the x and y components? So we have to choose our coordinates. So here is the x and y. Here is the x, and here is y. This is our origin. The acceleration is 6 units, 30 degrees south of west. By the way, again, you can call this east. You can call it east. This is north. This is south. And this is west. All right, this is west. So it's 30 degrees south of west. So here's west. If you're strictly west, you move this way. If you're 1 degree west, you're slightly this way. If you're 2 degrees south of west, you're this way. 3 degrees south of west, a little more. So 30 degrees south of west, so I go west, but then I have to drop 30 degrees this way. So 30 degrees south of west is a vector that looks like this. This is 30 degrees. And the size of that vector is the magnitude of acceleration. It's 6 units. 6 units. And the question is, what is the x component of this? What's the x component? And what is the y component of this acceleration? Let me show you basically two ways to do this. First, I'm going to redraw this triangle here. I will redraw the triangle. I think that is the easiest way. So here is a triangle. Where is the triangle? Yeah, here it is. Here is the triangle. Right. It's size 6 this way. This is 30 degrees. This is 30 degrees. And this is 6. Okay. And this is the acceleration. This is the acceleration. This is the y component of acceleration. I'll put it as AY. And this is the x component of acceleration. I'll call it AX. I only care about magnitude for now. I know the direction. It's in the negative x direction. And it's in the negative y direction this way. So first, the y is the opposite to the 30 degrees. So the AY will be the hypotenuse times the sine of the angle. Because opposite over hypotenuse is the sine, it means that the hypotenuse times the sine is the opposite. So I know that the y component of acceleration will be the acceleration itself times the sine of 30 degrees. And so that's 6 times the sine of 30, 6 times the sine of 30 degrees. Sine of 30, it's a nice angle, so that's 3 meters per second squared. The x component will be a times the cosine of 30 degrees, and so that's 6 times the cosine of 30 degrees, and that needs a calculator, so I'm going to use my calculator. And it will be 5.2. It will be 5.2. 5.2 meters per second squared. Those are the magnitudes. So I use this triangle. But now I know that the x component is in this direction, it's this way, and the y component is this way. So I will write my acceleration then as a vector. It will be, let me put manually, then you will put the minus sign here and the minus sign here, because from the picture, the y is negative and the x is negative. Okay, that's it. You can write your acceleration now as the x component of acceleration in the I hat direction plus the y component of the acceleration in the j hat, because this is the x, this is the y. So a can be written as negative 5.2 I hat plus y, that's it's also negative, so negative 3 j hat. And of course, those are in meters per second. Okay, in meters per second. Now, how do I do this just mathematically? What you can do is simply say, I like this way. I don't like to use the one where you just plug numbers without reflecting on them. But if you like, you can say the angle that the acceleration makes with the positive x-axis is what? 180 plus 30. So the angle will be 180 plus 30 degrees, and that's 210 degrees. And then you can just use it mindlessly. You will say AX will be the acceleration, A times the cosine of theta that it makes with the x-axis. So that's 6 times the cosine of 210 degrees, and that will give you negative 5.2 meters per second squared, and AY will be A times the sine of 210, not 30 degrees, of 210, and that's 6, I'm sorry, sine of theta, no, I will put 210 now, sine of 210 degrees, and that is negative 3 meters per second squared. We're going to do this several times. We're going to get practice with this. And so I will stop this video here, then we'll continue with the chapter and examples in the next one.